Yes, I think you have started. Yeah, perfect. Yeah, right. So what you see over here, you have all these circles with various colors, which denotes something called uh, actors. So actor can mean a person, it can be an organization, or uh, it could mean maybe a particular entity which is part of that network. So, and how it is interacting with other actors, that is denoted with these lines, right? So usually a network is a set of objects or nodes, and you have some connections between them. So in the context of social network, the nodes or those circles which you have seen, it can be people, groups, organization, countries, or any sort of objects, and which can be used by people, or maybe for some activities, or it can be just about anything, right? So usually we look at the structural aspect of this network. You have all these circles connected by these lines, and when you talk about social network analysis, we are talking about the structural aspect. So we have various methods that is not just theoretical, but also in a practical sense, it has got a major role, right? So when we talk about social network analysis, we can't get away without talking about this Barbasi scale-free networks. So this is a network topology which was named after the famous physicist, as well as maybe socio-computer scientist Albert Laszlo Barbasi. So this is a network where this network could be arranged in different forms. So that arrangement, that particular form of arrangement, usually we call by the name topology. So there are different type of network topology, and all of this will be governed by something called the power law distribution. So in other words, uh, degree distribution of nodes. So the nodes, as I mentioned, these are those circles which I have shown in the previous slide. So you have few nodes, you have some nodes, and in a Barbasi scale-free network, it basically follows a power law function, which means that few nodes have many connection, while most of the nodes have relatively few connections. So just think about any social network. Maybe as a common man, I may be having maybe 1,000 friends, but you take the case of any celebrity, whether it is a movie star or any politician, they'll have maybe 1 billion connections, right? So uh, there are few nodes that have many connections, while most of the nodes will have relatively few connections. So this is followed in all those social networks, right? So uh, for example, if we're talking about any other network, maybe they might be following something like a Gaussian or Poisson distribution, meaning that the nodes have similar number of connection. So this kind of scale-free property of Barbasi networks, it arises from a process called preferential attachment, where new nodes entering the network are more likely to attach to nodes that already have many connections. So this can be related to the concept where like the rich get richer and the poor get poorer, right? So many nodes with many connections become even more connected over time, while nodes with few connections remain relatively isolated. So this is a theory behind this scale free networks. So this you can find in many real world systems, including the internet, social networks, and you have something called biological networks. In all these aspects, you have these scale free networks. So scale free property has important implications for the behavior of these systems, maybe with respect to the robustness of the network, to random failures, or maybe efficiency of transformation of information from one node to the other one, right? So uh, in summary, I can say that Barbasi scale free networks are a type of network topology characterized by power law distribution of node degrees, right? And it's a very important aspect with respect to the research in network science. So, as I mentioned, social network analysis is a methodology used to study the structure and dynamics of social networks. And as with any methodology, it relies on certain assumptions in order to be valid and useful. And some of the key assumptions which we make is that uh, you have actors and relationships. So SNA assumes that social network consists of actors, which means individual, group, or organizations, and the relationships between them. These actors and relationships are the basic unit of analysis in social network analysis. And you have something called social ties. So the social ties between actors are important determinants of behavior, attitudes, and outcomes. So social ties can take many forms, as I mentioned earlier. It can be friendship, it can be communication, it can be collaboration, or it can be maybe simply a membership. And the network structure, the assumption that is made is that uh, the patterns of ties between actors important for understanding social phenomena. So network structure can influence the spread of information, the formation of social groups, and also ultimately the emergence of social norms. And another aspect could be there could be interdependence. So it assumes that actors are interdependent, meaning that the behavior and outcomes of one actor can affect the behavior and outcomes of the other actors in the network. We all hear this term called viral, right? Something has gone viral, some video has gone viral. So how it happens is maybe the action or behavior of one actor, it has influenced all the others, and they also start doing the same thing, right? So you would have heard of all this, maybe ice bucket challenge, which was a viral thing maybe a few years back, right? So this interdependence can lead to maybe feedback loops or cascading effects and other complex dynamics. And the other aspect could be context. So especially social networks are embedded in a larger social and cultural context, which can affect the behavior and outcomes of actors in the network. So contextual factors can include maybe social norms, cultural values, institutional rules, and maybe even historical events. So these assumptions what I've mentioned, those are not unique only to social network analysis, but they are important for understanding the logic and scope of the methodology. So by using these assumptions, so what I've mentioned is, one is social ties, other one is network structure, and the third one is context. So they're important for understanding the logic and scope of the methodology. So by using these assumptions as a framework, researchers can apply social network analysis to a wide range of social phenomena. You can even apply that to maybe spread of a pandemic or spread of a disease across a community, maybe diffusion of innovation, maybe, or formation of political coalitions based on certain criteria, right? So all these things are the uh, applications of social network analysis. So, talking about a historical perspective of these network analysis, as I mentioned, it has roots in sociology, with the early work dating back to 1930s and 40s. And one of the pioneers in the field of social network analysis was Jacob Morano, who developed a technique called sociometry, which involved mapping the social relationship between maybe individuals in a group. So Moreno's work was largely focused on small scale groups and did not yet use mathematical or computational method. It was mostly on small scale group. And in the 1950s and 60s, after the World War, sociologists began to apply more quantitative methods to study social networks. One of the key figures in this development was sociologist Harrison White, uh, who focused on large scale networks, such as maybe organizations and communities, and used a concept from computer science called graph theory and matrix algebra in maths to analyze the data. So that was the first time when some mathematical or computer science concept was used in a social network or sociology perspective. And as we moved on to 1970s and 80s, uh, this was a period of rapid growth and expansion of social network analysis, driven in part by advances in computing technology and also the availability of large scale data sets. So, sociologists, anthropologists, psychologists, and other researchers interested in this domain, they used social network analysis to study a wide range of maybe social phenomena, right from the spread of rumors to formation of social movements to maybe diffusion of innovations, so on and so forth. And one of the most influential figures in this period was the sociologist Mark Granovetter, whose work on the strength of weak ties. Later, I'll talk about weak ties, maybe after a few slides. So, he's the one who demonstrated the importance of weak ties in social networks for the diffusion of information and also the formation of social capital. And in the 90s or the early 2000s, SNA or social network analysis continued to grow and expand with new applications in fields such as political science, economics, and something called information science as well. So, one of the key developments in this period, early 2000s, was the emergence of online social networks, which I have already mentioned. And uh, maybe things started changing from that point, right? So this I've already mentioned. So the basic concept in a network analysis or social network analysis, you have actors, where these circles are the actors, and that can denote individuals, organizations, events, countries, or any sort of objects. And the relation between those objects, that is denoted by using these lines, right? And there could be various types of networks, or you can denote a social network in a variety of different ways. So which means that you have some data related to a society and you want to kind of plot it in terms of a network, that is using nodes and edges. So these lines are known by the name edges. So the lines which we have seen here, that is known as edges, and these circles are known as nodes. So nodes and edges, these two terms we'll be frequently using in this session. So there are different types of network. First one is known by the name ego-centered networks. They are a type of social network that focuses on the relationships of a central individual or ego, right? So in ego-centered networks, the ego is the focal point, and the network is constructed around the ego's personal relationship with others. So ego-centered, I'm sorry, ego-centered networks are commonly used in social network analysis to study the social context of individuals and also their relationships. So the network is constructed by asking the ego to identify all of the people with whom they have some form of social relationship. It could be friends, it could be family members, it could be co-workers, it could be some sort of acquaintances, right? So these people are referred to uh, as alters, and they're connected to the ego by the edges that represent their relationship with the ego, right? So ego-centered networks can be analyzed in various ways to gain insight into the social context of the ego. For example, if I'm calculating the degree of ego, so it can be calculated to determine the number of alters connected directly to the ego. So how many connections it has. So you have the center node here. I have one, two, three, four, five. Five other nodes are connected. I can say that my ego degree, my degree is 5. Right? And there are other measures also which can help you to get more insights about uh, this particular network. Right? And talking about other sorts of network, you have something called a complete network. So complete network is a network every uh, where every actor is connected to every other actor in the network. So actor in the sense node. So every node is connected to every other node. So that kind of network is known as complete network. So it is also known by the name full mesh network, another name. And they are the simplest type of network structure, but they can be very useful for understanding certain phenomena. And one of the key properties of complete network is that they have high levels of density, meaning the that a large proportion of possible ties between actors are present in the network. So this high level of density can lead to strong social cohesion and a sense of shared identity among the actors in the network. So complete networks can be used to study maybe diffusion of information or behavior through a network, or how a social norm is being formed, and how a collective action happens. Or for all these aspects, maybe if you have a complete network, that will help you to understand that. So despite their simplicity, complete networks can still be analyzed using a range of social network analysis methods and techniques. Maybe uh, that can be used to find out the influential node or influential actor in a network, or you can use it to some methods to identify subgroups or communities within the network. So how it is to be done, we'll see maybe few slides later. So in any social network, this is how it works. You have actors with points and relations with lines. So lines, you also call it as edge. So in general, it can be an undirected network, and sometimes it can be a binary network, and sometimes it can be a valued network. So there are various kinds of networks, right? So first we'll talk about what do you mean by a directed network. So you can see here the very first figure right over here. uh, from A to B, I don't have any direction. A is connected to B and B is also connected to A. I can take it in that way. But if I'm taking a look at over here, A is connected to B via this line, and B is connected to A via this line. And if I'm taking B to C, I don't have any connection from B to C. But from C to B, I have a connection. So wherever you have direction, such kind of graphs are known as directed uh, or directed networks. Not graph, I'm sorry. Such kind of networks are called directed network. So even in online social networks, you have a variety of uh, different networks. For example, if you think about converting your Facebook friends or your set of friends onto a network, so imagine that you are the center and you have different all your friends as different nodes, and you draw lines between them. So in Facebook, if I'm friend of a person A will be automatically friend of mine as well. So it is a undirected network. But if you take the case of Twitter, if I follow someone, that doesn't mean that the other person is going to follow me. So which means that that is a directed network. So these are the two broad classification. One is directed and the other one is undirected. And at the same time, you have something called a binary graphs. So binary graphs have edges that are either present or absent, representing a relationship between two nodes. So which means that here, if I'm saying A to B, I have a binary relation with that, which means that it is connected. But A to C, if I'm seeing, I don't have any direct connection. Of course, I'm connected through B, but I don't have any direct connection. So binary connections means that there is an edge between that two nodes. That is known as a binary connection. And there is another aspect known as valued graphs. So valued graphs means that you have certain value on top of that. For example, it is connected and you have some value. You can see here it is an undirected valued graph, where it means that A to B, maybe if I'm just representing this as the interaction between various nodes, which means that A to B had communicated one time, but B to C had communicated three times. Maybe C to D again one time, C to E four times, D to E or E to D maybe two times. How many number of interactions these actors had among themselves, or these nodes had among themselves. So when you have those kind of values, it is known as valued graph, right? So we have seen four things. One is undirected, where you don't have any sort of arrows like this, you have only the connection. And then you have directed graph, where you have arrows which represent the direction of connection. And then you have binary graphs, where you have only the connection, but no values, as I can I mean as I'm showing here. And then you have valued graphs where you have some value being represented, right? So so far we have seen the aspect of social network, like how social network data looks like. Now uh, it is all fine for representing it in terms of nodes and edges, or you have some circles which are connected together or connected using these edges, or maybe using lines. But at the same time, how do I represent this data? So in order to help us to represent this, uh, usually we make use of two kinds of things. One is known by the name adjacency list, and the other one is known by the name adjacency matrix. So right now, what you see here is an adjacent matrix or adjacency matrix. So how it is represent this? Imagine that you have a social network which consists of 5 different persons, and you are asked to create a adjacency matrix out of that network. So I'll write here all those things, maybe column row wise, A, B, C, D, E, and also just like you fill a crossword or a Sudoku, you will just write it with A, B, C, D this side also. So you have A, B, C, D on the left hand side, also I mean from top to bottom, also from left to right. Now after writing that, what we'll do is I'll just see whether there is any connection between A and A. A and A, there is no need to mention any connection. But if I'm asking whether there is any connection from A to B, I can just put that as 1. And whether there is any connection from A to C, A here and C here, I don't have any connection, so I won't fill that. But if I'm checking B to A, B to A, it is connected. So I'll just put a 1 here. Then B to C, I have some connection, right? So I'll put a 1 here. Then I have C to B. C to C and B are connected. So I'll put a 1 here. So like this, I'll just create a matrix, and that matrix is known as adjacency matrix. So if it is a directed graph, or sorry, directed network, it looks like this. You can see here A to B it is connected, B to A is also connected, and B to C it is not connected. So B here I don't have any value, it is an empty space. But C to B I have a value 1, right? C to B is 1. Now imagine that it is a valued graph. Instead of a binary graph, I have a valued graph, which means that on top of these edges, I'll have some values. In those cases, your adjacency matrix will contain those values. Imagine that I'm putting 5 here. So let me just imagine that I have a value 5 here, right? So if it is 5, A to B, I'll just write here 5. A to B, I'll just write here 5, right? So in this way, I can represent the social network data in the form of an adjacency matrix, right? And in addition to that, I also have other ways or means in which I can. Just now, I have seen a question from Ashish. I'm sorry, I somehow missed the chat. uh, protein interaction network using of blast and genomics. Yes, even protein interaction network is also kind of a network. So when I'm saying social network, for the time being our scope is only within social network, but the kind of protein interaction network that also has a similar logic, right? So you have various kinds of complex networks, not just social networks. There is something called a transportation networks. There is something called a citation networks, and that's the basis of how Google Scholar and all works, right? Yeah. So coming back to how you represent social network data, either you can go with this sort of an adjacency matrix, so you can see here, or you can go with something called adjacency list, right? So how it works is I'll just write each of the vertex here or each of the node here, and then I'll just write as a list to uh, which all other actors it is connected. So if I'm writing B, B is connected to A and C is connected to B, D, E, and D is connected to C, E, and E is connected to C and D, right? Or in other ways, I can even come up with an edge list, or sometimes I call it as an arc list also. So, which means that I can just write how many edge I have. So I have A, B, B, C, C, D, C, E, D, E, all these things, right? And if it is a undirected network, I can write A, B, B, A, B, C, C, B, C, D, D, C, like that. On both ways I can write, right? So these are the three ways in which I can represent uh, this wonderful concept called the social networks. So we'll take a very quick 1 minute break so that uh, I can make sure that you are with me, right? And as I mentioned earlier, if you have any queries, please don't hesitate to stop me. You can unmute yourself and ask, or you can put the query in the chat box as well. All right. So we'll move on now. So far we have seen how you represent the social network, and now we'll see how do you measure a network. So there are various metrics, there are various parameters, and there are various methodologies which can help you to measure a network. So measuring the network means you might be using various parameters, various metrics to kind of quantify your network. And one simple aspect is connectivity, so which talks about whether a particular node is reachable from the other one. So if I'm asking whether A, one second, let me take the pointer. So one second. Yeah. So as you can see here, if I'm asking whether A and E are connected, I can say that yes, it is connected. There is a because there is a path from A to E. So I can go from A, B, C, and then I can reach E. Or I can go even in this way: A, B, C, D, and E. Right. So if there is a path, then you say that those reach are, kind of connected. Right. So I'm just showing one more example on the right hand side. So usually connectivity has some basic elements, which means that you have a path, which means that it is a sequence of nodes and edges starting with one node and ending with another one. You may have a source node and you have a destination node, and you have a kind of sequence of nodes and edges through which you can reach the other node. So, and there is also something called a walk, which is a sequence of nodes and edges, and it may go backwards also. And sometimes you have certain paths which starts and ends on the same node. Such paths are known as cycle, right? So usually uh, what is the reason for this connectivity is that this will easily tell you whether whether two nodes are connected in any way or not, right? So there is something called a small world experiment, so where you have um, this was an experiment which was conducted by a scientist called Milgram in the early 1960s. So what he has done is he has written a letter addressed to somebody in US, and he has sent that to uh, one of his close friend. And the experiment worked like this: that friend can forward this letter to any one of his any one of his connection, and that friend will subsequently again forward it to any other connection. So the idea is, basically it should reach that final person where that letter is kind of destined to reach. So using how many people is it possible to do? So that was the uh, experiment. So in Milgram's experiment, it was found out that using 6% you can connect it to, or connect to any person in this world. That was the conclusion. And with online social networks, I think the degrees of separation, that is what, or six degree of separation is, right now it is maybe 2.5 to 3. So in a real network or in a normal social network it was 6, but in an online social network it is close to 2.5 or 3. So in these aspects, connectivity has got a huge role to play regarding the measurement of the networks, right? So the distance and number of paths, so all these things, right? And there could be different paths to reach the same node. Maybe uh, some things could be node independent, and sometimes you have some constraints where you can't go through certain paths, right? Without going to that path, is it possible to reach that the other node? So for solving those kind of problems, connectivity is one crucial aspect, right? So these kind of information network, it was there right from the early 70s. And the one you are seeing here, maybe it is an email exchange network, where how each of these actors has communicated among themselves. So in this aspect, you can see there is uh, some sort of a sub network here. You can see something is being circled here. So that is known as something called a cliques. So what is a clique is that it can be identified as a group of people who are highly interconnected, and those who share common interest activities or maybe social identities. For example, a study of maybe high school uh, might identify cliques based on shared interest, such as sports teams, music groups, or academic clubs. And alternatively, cliques might be identified based on social identities, maybe as a race, ethnicity, or gender. So once cliques are identified, researchers can analyze their characteristics and study their relationships with one another. So this might examine uh, the extent to which cliques overlap, or the degree to which different cliques are integrated within large social networks, right? So why I mentioned this, cliques are also one such parameter which can help you to measure certain aspects of the network, especially the potential influence of those set of nodes, or out of this, who is holding the power. If I reach to this person, then maybe this person is capable of reaching to maybe 100 million people, right? So these kind of analysis you'll be able to do uh, with this measuring of networks, right? And more importantly, whenever you talk about measuring the network or measuring the social network, we cannot move ahead without discussing this concept called a centrality. So centrality, the term, it means that a node which has maximum influence over the other nodes in the network, or in other words, that can be considered as the node which is of highest importance in that network. So there are various kinds of centralities in a social network, and based on the context and based on the purpose, uh, at least you can find 3 or 4 dozen centrality measures in social networks. And one of the most common thing is degree centrality, where it calculates the number of direct connections that a node has in a network. Specifically, it measures the number of edges or ties that a node has, which is referred to as a degree. So which means that if I have a sample network, say for example, if I'm taking this particular node and I have one, two, three different connections or three different edges for this particular node. So I can say that my degree is 3, right? So degree centrality is directly proportional to the number of edges a particular node is having, and you have variations in degree centrality like in degree centrality, out degree centrality, so on. Degree centrality is useful because I'm sorry, is useful because the nodes with high degree centrality, uh, it is often considered to be more influential or more important in a network. So this is because they have more direct connections to other nodes and therefore are better positioned to control or maybe spread information maybe throughout the network. So one common application of degree centrality uh, from a social network analysis perspective is the study of social influence and the opinion formation. For example, sometimes we use degree centrality to identify the most influential individual in a social network and then study how their opinions or behaviors affect the opinions and behaviors of others in the network. And we can also use degree centrality to study how information or opinions spread through the network by identifying the nodes with high degree of centrality and then examining how information flows through their direct connections. Or if you think from an organizational perspective, sometimes we use degree centrality to identify the most well-connected individual in an organization and then study how their connections and relationships affects the functioning of the organization, and then study how it could be rectified or how it could be maybe utilized in a positive way, right? So uh, sometimes even in a broader context, uh, 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 the you can understand degree centrality to identify weak points in a network, right? So who is going to be more vulnerable? So for example, if this person shares a fake news, maybe that is going to reach more people, and that will have maybe a disruption in the network, or maybe a complete spread of that fake news throughout the network, right? So these kind of applications are there for measuring degree centrality. Now, why we have different centrality measure? One reason is that maybe uh, what we want to measure or what we want to achieve from that social network. Based on that, your centrality measure may also vary. So, uh, as I mentioned, there are dozens of centrality measures, but we are going to look only maybe 3 or 4 such centrality measures in this session. And talking about the second centrality measure, it is between the centrality, which that it kind of quantifies the extent to which a node lies on the shortest path between pairs of other nodes in the network. So as I mentioned, if I want to reach another node in the network, I may have to find out the path. So I may have multiple paths. Out of that, which one is the shorter? So based on that, uh, this particular centrality measure is formed, right? So it basically measures the number of times a node lies on the shortest path between any other two nodes in the network. So let's assume uh, this particular node, what you see over here, let's say that is part of the for example, if I want to communicate from here to here and also from here to maybe here, in both these aspect, this particular node comes in between those nodes, right? So in that context, I can say that uh, I can say that here 2 times that node lies on the shortest path between the other two nodes in the networks. So in this way, between the centrality is calculated. How we calculate that, we'll not go into those details right now. I'm just trying to make you understand that concept of between the centrality. And uh, especially one of the common application of between the centrality is a study of network flow and communication. For example, sometimes you want to check uh, or identify nodes in the network that serve as important intermediaries or brokers by connecting different subgroups or clusters within the network. Because we all know certain persons, they might not be that much popular, but they might be knowing some people who are really popular, right? So these nodes play a crucial role in facilitating communication and information flow between different parts of the network, and their removal or disrupt or kind of, if we remove that network or that node from the network, that could have significant impact on the social network. So another application you can think about is the study of power and influence in social network. So uh, these nodes, as I mentioned, they could be strategically positioned. That is, nodes with high betweenness centrality are those nodes where uh, they are strategically positioned in the network, and they have the power to control or influence the flow of information or resources within the network. So these nodes may be able to leverage their position to gain access to important information or resources, or to broker relationships and alliances with other maybe nodes in the network. So uh, for example, if you remove that, then maybe that is going to have a lot of risk and challenges in that society, right? So it is a very powerful measure in social network analysis that can be used for to study network flow, power, vulnerability in a society, all these things. So you just identify those you calculate the betweenness centrality. There is a formula for that. I'll not go to that, but you calculate the betweenness centrality, and then identify the nodes with the highest betweenness centrality. Those nodes will have a certain role for this kind of a dynamics of the network, and also maybe for optimizing the functioning of a social network. For all these things, betweenness centrality could be used. And in addition to that, you have other centrality measure known by the name closeness centrality measure. So as I mentioned, based on what you want to achieve out of the social network, that is the reason why you have a different centrality measure. Closeness centrality measure is a measure that quantifies the degree to which a node is close to the other nodes in the network. So it measures the average length of the shortest path from a node to all the other nodes in the network. So in the case of betweenness centrality, we were just seeing, I want to find out the path between two different nodes, how many times this particular node is important when I'm just doing. So based on that, betweenness centrality is calculated. But in closeness centrality, you measure the average length of the shortest path from a node to all the other nodes in the network. So one common application could be study of information diffusion and dissemination in a social network. So sometimes you might want to understand, uh, or we might want to identify nodes in a network that are most likely to receive information quickly and efficiently. So these nodes may be able to leverage their position to disseminate that information more widely or influence others in that network. So closeness centrality can be also used to study the accessibility of nodes in a network. So sometimes uh, if you want to identify nodes that are easily reachable by other nodes in the network, what are the nodes? Those nodes. So you just calculate the centrality, closest centrality, and you should be able to find those nodes. And this is crucial to find or to understand the stability of the social network, how stable the society is, right? So nodes with high centrality, high closest centrality, may be more vulnerable to failures, because their removal, for example, if I'm just removing that node from the network, then that can have greater impact on the overall structure of the network. So as I mentioned, closer centrality can be used for studying a variety of phenomena related to information diffusion in a network, how a news is being spread, or with respect to accessibility, right? So by identifying the nodes that are close to the others in the network, we can gain insights into the structure and dynamics of the network, and also to develop strategies for optimizing the overall functioning of that social network. So when we in general, when we talk about network analysis or social network analysis, there are various network properties, which some of it uh, are quantitative measures, and some of them are qualitative measures. So structural and network properties, they basically refer to the characteristics of overall structure of a network, as well as the patterns of connections and interactions among the actors or nodes within the network. So these properties can provide important insights into the organization and dynamics of social networks. And ultimately, this can help researchers to better understand how information, resources, and other forms of influence can be distributed within a network. So, some of these network properties we'll just take a look. One thing is a network density. So, network density refers to the proportion of all possible connections that are actually present in a network. High network density indicates a tightly connected network. There where many nodes are directly connected to one another, while low network density indicates a sparsely connected network where relatively few nodes are connected to one another. Right. And there is another structural property known by the name clustering, which refers to the extent to which nodes in a network tend to form groups or clusters. So, high clustering value indicates that nodes are more likely to get connected to the other nodes within the same cluster than to nodes in the other clusters. Right? And we have already seen this measure called centrality, so I will not talk much about that. And earlier we have seen what is a clique. So clique is also one of the quantitative structural uh, network property. And there are many qualitative measures also. So for example, earlier I mentioned about strength of ties or weak ties. So these are kind of refer to the intensity or closeness of relationship between the individuals or groups in a network. So that closeness you can't quantify, right? So it is like asking like how much you like a particular person. Like you it's not possible to quantify, because it's a qualitative thing, right? So the strength of ties can be measured in different ways depending on the nature of the data and also what exactly you're looking. So some common measures of tie strength or strength of ties, it includes maybe if you take into account frequency of interaction or duration of interactions or what is the emotional intensity, right? So these parameters you put it together, and then if you try to understand, maybe to some extent you will be able to tell what is the uh, strength of tie in that social network, right? So when I'm talking about frequency of interaction, it means measure the measure or the number of times individuals or groups interact with each other. For example, in a network of co-workers, for example, you think about social network sites such as LinkedIn, right? It is a network of co-workers or network of professionals. So the frequency of interaction between two individuals might be measured by the maybe number of messages sent between them, or the number of meetings they attended together, or number of times they collaborated on projects, right? So all these things can mean or can be uh, can be identified as interaction, right? And talking about the duration of interaction, so this measures the length of time that individuals or groups interact with each other. So for example, in a network of friends, duration of interaction between two individuals might be measured by the length of or the time they've spent talking on the phone, or length of time they spend hanging out together, or the length of time they spend participating in in some shared activity, right? So all these things can play a role in this maybe duration of interaction. And talking about emotional intensity, this measures the emotional closeness or intensity of the relationship between either individuals or groups. So it could be measured by the strength of their bond, the degree to which they support each other emotionally, or the degree to which they rely on each other for emotional support. So all these are qualitative in nature. And there are a lot of aspects in this direction. I'm not talking about all of them, but one thing I want to kind of in a nutshell I want to highlight here is there are quantitative measures such as density, size, centrality, uh, maybe cliques, then different kinds of centrality. And at the same time, you have certain qualitative measures which could be calculated uh, by taking into consideration various aspects. For example, trust within a network. So uh, sometime back I have worked on a work related to that. Basically, how do I measure the trust of a person, right? I'm in a social network, and if I get a new friend request, how do I ensure that that person could be trusted or not, right? So both from a theoretical as well as practical sense, these kind of things, they are more or less qualitative in nature, right? And this basically gives you a theoretical understanding of how social network analysis could be done, right? And uh, as per our agenda, we'll just see few other aspects of maybe the research aspect of social network analysis, and specifically online social network analysis, because right now, mm, we do social network analysis on this using this online data. So that's why we call it as online social network analysis. And you have variety of users existing over there. So there are you can find diverse usage of online social networks in the last decade, for coordination, for self organization, during different types of social activism. For instance, you would have heard about different hashtag maybe Black Lives Matter, or hashtag Me Too, or hashtag Occupy Wall Street. So basically for maybe eradicating some stereotypes or eradicating harassment. So for all these things, you have different hashtags which had gone viral. So online social networks had provided a valuable platform to support and rebuild communities uh, after through these activities. Or take the case of natural calamities or natural disasters. There also you have this online social network playing a crucial role for all these rehabilitation and rebuilding of communities, right? Now, at the same time, uh, all these online social networks have facilitated the amplification of malicious agenda. Say, for example, harass and bullying others, or spread disinformation for alternative narratives, or for to manipulate public opinions using fake news during elections. So all these things are also the other side, right? So one thing that has happened in the last 3 4 years is that even in a computational aspect, there has a lot of changes that has happened. Because how we deal with data, if you think about the old 1960s, that time we were using only database technology, maybe storing data as records which were linked to one another. And each of these thing could be accessed by using maybe a pointer, right? Then you had a thing called a relational, where most of the database even today they work on that. So where it was more efficient for storing, managing, or retrieving data from tables, right? And also in the earlier 2000s, there was a development of database technology which was inspired from this sequel, which we call it as NoSQL movement. So the objectives of that this era was to create scalable technology that stored, managed, and queried on non-tabular data. So tabular data is very easy to deal with. You can imagine that as an Excel sheet. But in the case of non-tabular data, you may have other forms of data. And one thing that has started happening in the last 3 4 years is something called the graph thinking. Specifically, there is a proven observation time lag between all these technology. You can see here, I've put it here like in a time period of 20 years, right? So there was a time lag between 1980 to 2000, and there was a 10-year lag between maybe the first paper on that technology, and then implementation in a real aspect, right? So right now we are going through a stage called graph thinking. So being able to see graphs across your data is the same as recognizing the complex network within your domain. So even social network is also considered to be complex network. So within a complex network, you will find the most complex problems to solve, and most high value business problem as well as opportunities are in these complex problems. Because why I say this is that data is no longer just a byproduct of doing business. Data is increasingly has become a strategic asset in our economy. And uh, any big companies you consider, they have graphs. This graph thinking approach, it has started penetrating, and obviously that is going to uh, do more from a computing perspective, right? So this is the significance of the social network analysis also in this context. Basically, you have this network, and then based on that you can solve it. So you take the case of any e-commerce website. So all you have a whole set of this kind of a network related problems there. So the moment you order a particular product in Amazon, and how it reaches your home, till that time you have various uh, network related problems that is happening. So there you have uh, transportation network, you may have logistic network, so different kinds of network which is being used in that domain, right? So I'll not say much about this. Very quick break on this. All right. So the next thing, we'll just focus on some of the possible research aspects of this social network analysis, and why there is a lot of significance with respect to uh, big data, and also with respect to the social network analysis at, I'm sorry, in this context. Because you have this unprecedented amount of data that is leveraged by all these big companies, whether it is Amazon, Apple, Facebook, Google, or Microsoft. All of these people, they gather huge quantities of data, right? So social network data is one such data which qualifies the definition of big data, because you have around 4 billion active social network users all around the world, and 5 billion contents are posted every day, right? Or and you have a variety of different data happening. You have text, image, video that is happening, and the variability, that is heterogeneity of the data, is also very very different. So in all these aspects, it qualifies as the perfect data to be called as big data, right? So data produced by users who decide to share almost everything. It could be photos, comments, political opinion, recipes, food recommendation, travel, positions, what you're feeling, all these things. So they indirect or directly or indirectly, it is getting ingested by these social networking or network sites, who provide or who enrich the original user data by adding semantic metadata, statistics, and usage patterns, which kind of gives a feeling that okay, I should post more, or I should again scroll down more, right? That kind of a feeling, right? So in this context, there are various aspects, especially in social network analysis. There are something called a content oriented approach, where you also take a look at what exactly the data is. And then the other aspect is you also take a look at something called network oriented approaches. So we'll just talk few things about the network oriented approaches here alone, because in a the kind of analysis which we do, that will have only this network oriented approach. Because uh, how it differs is that, for example, if I'm doing some social network analysis, and uh, I'm just only seeing the overall network, that is, I'm only seeing the overall uh, structural methods only. In that case, it doesn't matter what I'm posting. So that aspect is known as network oriented approach. So network oriented approach, they analyze all these big social data based on nodes or entities and their relations within the network. So network oriented approach, usually it is again divided into embedded learning and community learning. And you can find a lot of research papers on these topics. And some of the papers, they present this embedding learning, which obviously they focused on extracting valuable information about users and nodes inside a network. And you can use that for other things like influence analysis, or how information is diffused in a social network. And you can even use it for friend recommendation, and the technical term for friend recommendation is known by the name link prediction. And social influence, we all know an individual's ability to influence another user in a network. The more influential a person is, more followers he or she will have. And when you talk about this embedding learning approach, it aims to analyze a network based on users and their features, and the model the process of information diffusion on online social networks through learning that users characteristics, and accordingly decimate information among users. So embedding learning approaches try to find out the influence of different nodes in the network by identifying the position of a node in a path or number of paths in which it occurs. So the earlier things what we have learned, that is centrality, all these measures can play a role in this to learn how this works. So maybe in the aspect of predicting the underlying diffusion process, for example, I post something, how that is going to get viral, or how that is going to travel across the social network, right? So uh, there could be to do that, there could be different methodologies. And usually you uh, call it as graph based methods, non graph based methods, and the third thing is explanatory. So you can find all these three things here. So graph based and non graph based methods are kinds of predictive models, which by investigating the previous information propagation, the information dissemination is predicted from maybe from a spatial temporal point of view. For example, if I'm in a particular location, last time I have posted this, and maybe the next time when I reach the same location, you may get a same uh, kind of a review. See, last time you have done this, or as a memory it may show, right? So these kind of aspects, how it is being done is based on the previous historical information. And graph based approaches focus on static and graphical structures of a network in which information is transmitted and predicts who influences whom. So in this approach, each node can be activated or deactivated, such as maybe there are methods such as independent cascades or linear threshold. I'm not going into that. So there are various aspects related to that. And in addition to that, there is also something called a community learning. So as I stated earlier, social networks comprises a set of nodes or vertices in which nodes stand for users and individuals, which are associated with one another through numerous edges that represent their relations and interactions. And community is referred as groups of individuals who have similar interests, attitudes, or common characteristics. So, from the social aspect, detecting groups of individuals in the network on structural and topological properties known as community learning, which is crucial for various perspectives in society, such as business or recommendation systems. Right. So, you would have seen in Amazon, like you buy something and it will suggest you people who have bought this particular product has also brought these things. Right. So, thus it leads to innovative approaches for identification of communities that can be carried out in a micro or macro network using these structural features, right? So that is known as community detection. The assumption is that people in one community interact more with another because of the similarity of interest among them compared with the other communities. So the network is divided into various communities, and in that also you have a lot of classification happening. I'm not going into that, just trying to give an overview. And in community learning, after identifying the cluster of nodes, the number of clusters is determined. A cluster is mapped onto a community, then the probability distribution of interaction among users and also within and among the clusters is estimated. So there are different community learning approaches which can be categorized into node based or group based. And node based approaches are carried out based on properties of network nodes. So what is the centrality, or what is the click value? Based on these, maybe I'm just suggesting few measures. And since similar nodes belong to the same community, based on node degree, node similarity, node reachability, all these things could be considered on this node based community learning. While group based approaches do not regard characteristics at the node level, and they consider kind of characteristics uh, and connections of the whole group and network by recognizing uh, different robust communities or hierarchical communities within there, right? So uh, I'm not going into the depths of what each of these things mean. I'm just trying to give you a very very broad overview, right? So how usually research is done in online social network analysis. So usually, as a person who has been working on this domain for the last 10 to 12 years, there are certain possible questions when you ask in a uh, OSNA perspective, right? So usually, uh, there are four dimensions of social network analysis, right? So first thing is, what can I discover? This is the most uh, classical and very much studied characteristics in social networks from the past century. Different methods and models from social science, and more recently from uh, even from science and engineering, have been used to discover new knowledge and patterns that could be in the form of network structure, topology, uh, information flow into a network. So usually we define this feature as a dimension related to the capacity of algorithms which we are going to use, or methods which we are going to use, or techniques basically to gather knowledge from these social networks, right? So uh, and the concept of value as the knowledge or discovery or knowledge or pattern discovery capacity of any method, it can be easily extrapolated to the area of social network analysis also, especially with all these uh, domains such as big data analytics, data mining, predictive modeling, data visualization. You have a lot of opportunity to kind of do things, especially with respect to data mining. You'll be able to find patterns within the network, and that will help you to know more about that, right? And the next question is, what is the limit for the kind of research I'll be doing over here, right? So the aspect could be, for example, especially in the social network, online social network scenario, you have a lot of data being ingested, and sometimes you may not be able to consider certain qualitative aspect, which will be one of the limitations in that aspect. And also, it is a good practice to integrate things that are related to that. For example, you think about uh, any any online social network, they kind of provide you variety of services, like sharing photos, videos, music, or think about microblogging like Twitter and all. So in addition to the service provided by the online social network, all of them allow different kind of interaction between the users. That, for example, in Twitter's users can follow the other users, where in Facebook they are just friends. or in Instagram also it is the same thing, and different actions over the content published by the user. Only that thing varies, right? So what kind of data can I integrate? The measure would be equivalent to the maybe the concept of variety in big data. So there are different V's in big data. Again, I'm not going into that and confusing you. So there are different measurement that will take into account maybe the number of different types of data, number of different online social network you are considering, and the presentation of this data into the model, right? So whether you are considering only the only the photos, or only the textual data, or only the video, so all these things matters. So and here basically out of this, what insights can I show to a user, right? So there is not a consensus about what is the best strategy for visualizing networks. So there are advantages and disadvantages for each technique. So there are things uh, like Hive plots, which is part of Apache Hive projects, where uh, for example, if you're working with a large network, such as earlier somebody asked about a biological network like protein protein interaction. So in that you have a huge network and you want to visualize that, there are tools such as biofabric which will uh, represent it in a better way. Or if you have a large graph and you want to just drag and drop the data onto something, you have something called a pivot graph, which help you to summarize the position, size, shape, orientation, color, saturation, texture, all these aspects onto that graph, right? So these are the various research directions possible in a online social network analysis. And talking about the domain in which this could be applied, there are a lot of research papers that study the applicability of online social network in health domain. So for example, new possibilities beyond the traditional doctor to patient paradigm. So many patients with different diseases are now using maybe social network to share experience. So it has some pros as well as cons. Uh, maybe there are numerous health related behavior that might easily spread out in OSN. For example, smoking, alcohol consumption, or drug use, right? So several research studies have been appeared which analyzes this effect from a social network analysis perspective, right? So and the other aspect could be marketing, where you have different brands and customers uh, coexist, where all of them can interact. You would have uh, come across different war of tweets or war of Facebook posts between different multinational companies. Like maybe sarcastically, they used to do that. So obviously, it increases the visibility of both the brands, right? So you can even say that there is a clear contribution of social media in the generation of new word of mouth, right? Which stands for electronic e-mom or e-wom, where like electronic word of mouth. Using social media, customers are able to express their opinions about maybe specific products. And in that also you can apply this social network analysis. And then you can think about tourism and hospitality, where uh, like hotels and tourism destination, they use it for marketing purposes. And there is an increased significance for social network analysis. Even from a security aspect, there are a lot of application, not going into much of that. Politics, for getting the opinion of different people and understanding what exactly to which side a particular person will be aligned, right? So one famous case study will be the Arab Spring rise, which happened in 2011, and also uh, uh, the US presidential election, especially the Obama's campaign in 2008 and 2012, that marked the beginning of like how social media might affect citizen and participation in political life, right? So also, maybe not from a social network aspect, from a social media perspective, there are also application where to detect hate speech, to detect maybe political polarization. For all these things there are a lot of application, right? And more importantly, for detecting fake news and misinformation also, you can make use of social network analysis. So maybe main risk about fake news is related to the concept of intent. uh, that is, the goal of any fake news is to persuade consumers to accept biased or false information, usually with a maybe political message or influence. So this goal and the past propagation of message in online social networks made that, for example, the most popular fake news even more widely spread on Facebook than most popular authentic mainstream news during US presidential election in 2016. So everybody might be remembering about the Cambridge Analytica scam and all, right? So fake news detection is also a promising domain where a lot of significance for social network analysis plays, or social network analysis also has, right? And definitely the future of social network analysis is also very bright. So how we can say that is that there is a company called Gartner, which is considered to be a technology driven company where they make these future prediction, right? So if you think about some of their graph, it clearly tells digital marketing has got a lot of significance in the upcoming years also. So I'm not going into these aspects much. So instead, uh, in a nutshell, I can say that these are the key issues which could be addressed using social network analysis in online social networks. So, uh, especially profiling anonymous identities, maybe the cases for bullying or harassing, it mostly comes from anonymous profiles. So the impact of such virtual anonymity leads to a lack of accountability and trust. So how we can find out these anonymous identities using social network analysis? So that is one of the key issues which is relevant even today. And also basically spreading of social bots. So it's not clear how many users of online social networks are actually human users versus social bots. So for detecting that also, various social network analysis could help to detect that. And spreading of malicious content already I mentioned. So basically, to make the world a better world with online social network, definitely OSNA, or online social network analysis, has got a great role to play. And the intent of this session was to give a brief overview about how or what is social network analysis and how it could be done. And the conclusion is like this: there are enough opportunities in online social network analysis, and especially if you wish to work with any of the programming languages, definitely there are a lot of opportunities in various companies, because there is an increased relevance in the research of OSNs that has happened in the past 1 year or so. So I'll just mention few of the references which I've used. So from this onwards, we'll be moving on to the hands-on session. So in the meantime, if you have any questions related to what we have seen in the last 1.5 hours, I would be happy to uh, answer that. If there are no questions, then we'll directly go to the hands-on session. So for that as well, I'll be posting some materials, some links over here. Just give a second. Give me a second. So for easy navigation and also your understanding, I've prepared a handout for the session. You can access that right over here. So you can just tell me whether you're able to view that page when you're clicking on that. It's a handout made for this session. For the next 1.5 hours, we'll be working on that handout. And there are some data sets which we'll be working with. And that link also I'll just post here. Yeah, so uh, can someone acknowledge I've posted two links? So the first one is related to the hands-on session, and the second one, for that hands-on session, we'll be using some data sets. So if some of you can, any one of you, if you can acknowledge that, it'll be great.
Yes, sir.
Yes,
It
sir.
accepts.
Yes.
Okay, you're able to view a page, web page, right?
Yes, sir.
Yes, sir.
Okay, fine. Right. So in that case, we'll just move to. So just before beginning, one question. I'm going with the assumption that all of you know the basics of R programming. Hope it is fine.
Yes, sir.
Yeah. So if you want to do this analysis along with me, you are most welcome to do that. And to work with R Studio or R within a browser, you can just click on this link, that is posit.cloud. So which means that I'll just paste it here. The link I'm just pasting. So this sites, it gives you free of cost the R capabilities within the browser. So you can just sign up to this particular website. Just click on sign up, and so there is a free thing available. So you can just sign up with either your Gmail ID or your institution ID. It doesn't make any difference. So I'm just signing up here. So once you sign up, you will get something of this sort. And here, for example, I'll just go to some session which I've already created some time back. So if when you sign up for the first time, you may not have that workspace. So you may have to create a new workspace here. So it may take a little time. So once you successfully log in, sign up and then log in, you will be able to find the particular. Okay, here I'll just stop it. So you can write your R code where your cursor is here. So if I'm just putting 2 plus 2, it should give me 4, right? So like this, you can work along with me also, right? So in a similar way, uh, here this is a R Studio portal I've created here for the users at IIT Kottayam. So I'll be working on this, but the same capabilities you can find it in this posit.cloud as well, right? So you can take a look at the handout link. So this basically we'll practice a little bit of social network analysis, and we'll try to understand the relationship and interactions between individuals and organizations based on some toy dataset. And in order to get started with this, I'm sure you are aware of different packages in R programming. So right now the screen, what you're seeing is nothing but the R Studio. So here, and uh, the one you see here with the cursor, that is known as an R console. So you can type your R programs or R statements right over here, and you should be getting this. So if I'm just putting a is equal to 2 and print a, that will print that particular value, right? So uh, since all of you know the basics of R, I'm not going into that. So here, as you might be knowing, R is a community driven project where you have lot of packages or lot of libraries which can help your or help your job a lot more easier. So one such package uh, or a set of packages we'll be installing for this session. So you can find in the second under the heading getting started with R for SNA. Under that you can find 4 different packages. I'm asking you to install. One is known by the name iGraph. So how to install package? You can just go to tools. So in POSIT also you have that tools, install packages, and here you can just give iGraph. Click there, click on install, and it should start installing. Maybe it will take a little time. Yeah, so now it has started installing. So you can install all those packages, especially iGraph, then you have ggraph, then tidygraph, and then you have vis network. So all our uh, all our coding will happen using these packages only. So it may take a little time to get it installed. So you can see automatically it is getting installed. And once it is installed, to make sure that things are okay, I can just make use of a command called library. And within that, I can just mention the package. So library of iGraph. So it has not given me any error message. So which means that my installation of iGraph is successful, right? So now what I'm going to do is here you can see the handout. So I've put this line of code, a library of iGraph. So now here, what we are gonna do is, earlier we know that you can create a social network either from a adjacency matrix or from an adjacency list, right? So just to recap that, let me just bring you that to that slide. If you remember this particular slide, these are the three ways in which you can represent data, right? So here, if I'm going back here, sorry, yes. So I need to create the data uh, in this form so that basically I can create a network from that. So here, I'm sure since you already know the basics of R, in R usually you can store things either as a data frame or as a matrix or as a list, or there are even other data structures available. For the time being, I'm going to create a data frame here. So edges, I'm just naming that as edges, and I'll just say it as data dot frame. And here I would just I'll just create a social network that is from, I'll give a set of people name, and another column I'll create, and that I'll call it as again another set of people's name, right? So you can, I'm just giving some random name, Alice. I'm sorry, this comma should come after the quotes. Now we have Charlie, and lastly you have Eve, and another column which is here again I will say Bob, again I'll say Charlie, and then I have Dave. I'm just giving some random names. You can give anything of your choice also here. I'm just creating a dummy social network, right? Alice. Sorry, somewhere I have misplaced that comma. That is the reason. You have 4 there. Okay. In the earlier thing, I have missed one name. I should have equal number, right? Now 1, 2, 3, 4, 5. Bob, Charlie, Dave is missed. Okay. Okay. Yeah, there is a problem with that double quotes here. I'll put double quotes. So now if I'm seeing what is this edges, now I have a table, right? Which means that I'm just denoting two columns like Alice and Bob, they are friends. Bob and Charlie, they are also friends. Charlie and Dave, they are also friends. Dave and Eve, they are friends. Eve and Alice, they are also friends, right? Now, if I create a data frame of this sort, this iGraph package can help me to convert this into a network. So here I'll call that as a graph object. So here this social network I am calling with the name graph object. So I'm going to create a graph object. So how I can do that is I'll just say graph from data. So here you can see graph from data frame, and I would just inside the parameter, I would just inside the parenthesis, I'll just give edges. Now if I want to see how this network looks like, I'll just say plot of G. So that has given me a graph of this sort, right? So the arrows are pretty fancy that we can change later, but this is our first social network created in, using our programming, right? So this has created a simple network with 5 nodes: Alice, Bob, Charlie, Dave, and Eve, right? Okay, maybe one possible.
Sir, I think you should get a
Yeah,
circular graph on this, because
yeah.
the fourth number,
Mm.
one Dave is with a small case and the other one is with a large Dave.
Yes, yes,
So
yes. No,
change that
here
to
even
circular.
if it is not a circular, also it is okay. If I'll do one thing, I'll just change it this into the same thing so that it will denote the same person, right? Right. And now if I graph edges, and now if I plot it. So the earlier graph, I had Dave as two separate person. That was the reason why it had given me as a kind of a straight line graph. But here you have a ring kind of graph, right? So the intention was to create uh, a network or a social network using this iGraph package, right? Now, so here what we have done is we have created some data on our own, and then we try to kind of plot it, right? Now, but usually, if you want to do social network analysis using R programming, you usually store data somewhere and you are just importing that data, and you might be working on that data, or you might be collecting data from a social network, online social network source, and then you may prepare it in a suitable format. So there are certain popular formats which are used for social network analysis. As I mentioned, one uh, is adjacency matrix. Yeah, adjacency matrix, and the other one is adjacency list, and the third one is edge list. So the data can be imported from different sources, like either it can be Excel spreadsheet, sometimes it could be a CSV file, which is comma separated values. So in the Google Meet, that chat box, if you check the second link, I've put two such files over there. For the time being, we'll not look into that, but at a later point in the same session, we'll go back to that. So basically, for visualizing graphs, it will help us to uh, kind of import from these files, and directly you can plot it. And using these iGraph, we will calculate various network measures like degree centrality or betweenness centrality, and even how what is the clustering amount, or how we can quantify the clustering, and all these aspects we will see in detail. And in the meantime, we can also install some more packages like ggraph, which will help us to. So for installation, it will take little time. So once it gets installed, we can. So one thing I want to mention here is, once you install a package, next time if you're using the same console, you don't have to install it again. You can just call library that particular package, and you should be able to work with that. Since we are doing it for the first time, that is the reason why we are uh, installing that particular package. So installation takes a couple of minutes. Yes. And to make sure it works, how do we ensure that? It is just by typing graph. Yes, it hasn't thrown any error, because how it is going to throw an error is, for example, I haven't installed the package tidy graph, but if I'm asking library of tidy, uh, here already you have tidy graph, so I can't show here. So imagine that if it is not here, let's say uh, this is another package which I haven't installed. So then it will clearly tell me there is no package called imine right now installed. Right. So in the similar way, like ggraph, you can also install tidygraph. I'm not showing that. So since it is already available here, I'm not installing again. So tidygraph. So using these three things, we will kind of visualize all these different kind of social networks. So Uh, along with these packages, there are certain data sets uh, which comes along with these packages. One such data is high school data set. So it is a data set which shows the friendship among high school boys uh, in the year 1957 and 1958. And you have the format of the data set. It is in this way. You have three columns: from, to, and year, right? So we'll just take a look at this data set by using the view function high school. That this comes along with ggraph package. So this is the data set. You have person 1 connected to person 14. You have person 1 again connected to person 15, again connected to 21, and you have the year also, right? And this has around 506 rows, and you have a total of 3 columns. So let's see how you can plot this, right? So we'll see various packages which can help us to plot this, but using this ggraph, how we can plot this. So um, right now, we'll do one thing. We'll first plot it using the uh, earlier plot function. So earlier, the command what we have used is, we have tried to create graph from data frame. So same thing we'll do here also, from graph from data frame, and the data frame here is high school. We'll just try. I'm not sure whether what we're gonna get. So then we'll just plot G2. What does it give me? It gives me a highly. It is giving me some values, but it is not conveying me anything. It is completely cluttered all over the place, right? So using the simple plot function, I'm able to get it in the form of nodes and edges, but unfortunately, it is not conveying anything to me, right? It is completely uh, cluttered, right? So what we're going to do is using this G graph, using this G graph, I'll try to plot this. And using this G graph and tidy graph, we will plot it. So let us try that. So here, what I'm going to do is I'll just create a new graph object. So here, I can also make use of another function as underscore tbl underscore graph, right? So using that, I can create a graph object, or I can use the same thing which I have created earlier also. So I'll just show this also as table. The table is converted into a graph, and here I would just say high school, right? So if I'm just printing G, it is giving me something of the sort. If I'm just using G2, then it is giving me as an iGraph object, right? Since we are making use of tidy graph and a G graph, that's the reason why I'm not making use of that, uh, not making use of that iGraph object, right? So here, using this, how do I plot it? How do I plot a good graph? Let me clear all these things so that I'll just. So what we have done now is I've just created G as a graph, that is that table, that particular data set which you can see here, that I've converted it into a, a graph object using as underscore tbl underscore graph. And now I can call the gg graph function, and here I can directly tell what particular graph object I have here. So I'll just mention G, and I can mention the layout of my graph. So the layout, I will just mention KK. So there are different layouts available. Later you can explore that as well. And here, uh, if I do that, what do I get? Okay, I will not mention any layout. I'll just simply pull G graph, and I'll just. So I think it's, since being it has around 500 nodes, it is taking a little bit time. So for the time being, we'll not see that. We'll just try to uh, kind of do some more or add some more parameters onto this D graph. So I just mentioned layout is equal to KK, and
Sir, sorry to
yeah,
interrupt you.
yeah, please go ahead.
I'm getting a error when I'm trying to do the function as underscore table graph.
Have you installed ggraph package?
Yes, I did.
What
I
about
all of them.
sorry, not ggraph? What about tidygraph? Tidygraph, I haven't shown the installation because already it was installed in my console.
Yeah, I did. I so when I went to the social network analysis using
Okay,
the file that you sent, I
yeah,
ran all the four codes.
all the
In,
four, yeah.
so,
So
but
what is the error? Can you tell me?
it says that error in as underscore table underscore graph high school could not find function.
It means, have you called this particular line of code, library of ggraph and library of tidygraph? Library of tidygraph. And then if you execute, I think you should get it.
Wait, let me just do
Yeah,
it. 1 second.
yeah.
Yeah, I'm not getting an error anymore. I'll just quote
Yeah,
the.
yeah, which means it is solved, I guess.
Yeah, yeah.
Yeah,
Thank you.
yeah, okay, right. So here we'll plot it using ggraph. So the layout I have mentioned as KK. Now, if you have tried out plotting graphs using the ggplot package in R, usually you can first go for a normal graph, and on top of that you can keep adding layer to that particular graph. Or in this case, you first create a normal network. On top of that, you can tell the features on which you can add things layer wise. So that could be done by giving a plus here. So and I would say uh, specifically what kind of edge I'm looking for. So there are different kinds of edge here. I would go for edge underscore fan, right? So draw edge as curves of different curvature. So these things, I can go with any of these things. I'm just going with edge underscore fan just as a demonstration purpose. And another thing is that I can even give some more aesthetics inside that, right? So here to make the graph more visible, one thing I can add here is I can add an alpha value. So what is that alpha? For the time being, I'll not explain. And I would say after underscore stat. Yes, for the time being, I'm not going into that, but I can also say that no need to show any legend here. That legend, I'm just keeping it as false. And on top of that, I would just say geom underscore node underscore point. So just show nodes as points, because you have so many nodes here. If you are going for a circular thing, it is going to make your graph a cluttered thing. That is the reason why I'm saying you just plot the nodes as points, right? So here what we have mentioned is in any network you have uh, nodes as well as edges. So here what I've mentioned, I've just initially called this GG graph, and then I said, okay, make use of the data inside G and let the layout be something. I've just put as KK. You can go for any option. Later I'll show with a different option also. And then layer wise, I need to now tell how my edges should look like or how my connection should look like. And on top of that, I've added how my node should look like. So after adding these things, let me just execute it. So I got some graph with some warning. So you can see the graph. So it is far better than what I've earlier got, right? But still it doesn't convey anything, right? So now what I can do is I can even make this graph a better one. So what I do is the same code. Now on top of that, let me just add something, phase it underscore edges, right? And here, based on here, if I have two different graphs, that will convey more things, right? So I'll just put year as one thing here. So here, if you remember this data set, I have from, to, and also then year, right? So here I'll put as a uh, uh, as a something like I want like two different graphs for each of the year, right? So I would just put it. Yes, here we go. Now 1957, I have a graph. 1952, sorry, 58, I have another graph. Now, this graph is very boring. It is not at all attractive. Now, if I want to make it attractive, there are certain themes available, which I can add again on top of that. So again, same code. On top of that, I'll just add one more layer. I'll just say theme underscore graph. So theme underscore graph under ggplot. And I would say maybe I can mention what there are so many parameters here. I can see here foreground, background. Right? I'll just use few parameters also. If I don't use also, it will go with the default things. So foreground is equal to, I would just give a color here, maybe steel blue, right? And foreground text color, I would make it as white. I can go with any color. For the time being, I'm just putting it. Oh, here we got two different graphs, right? So here we got this graph. This creates a network graph or a network with custom node and edge colors. So making it easier to visually distinguish between different nodes and connections. But even now also, since I haven't put any labels, I can't I'm sorry, I can't distinguish between each of those actors or each of those nodes, right? So this is how you can plot a particular network using um, this GG graph and also using this tidy graph. So right now, just to recap what we have seen how to create an iGraph. iGraph is a package, and if I have some two columns, I can either convert that uh, into a iGraph object using graph underscore from underscore data underscore frame, and that will create you an iGraph object, which we have earlier done. The very first line of code. I'm so sorry, I just closed it by mistake. Just give me a second. Yeah, yeah. So the very first graph, if you remember what we have plotted, let me just show you. So this was the very first graph which we have plotted using iGraph package, and by converting that into iGraph object. And then what we have done is when you have more number of graphs, maybe just using the iGraph may not be sufficient, or just using the plot function may not be sufficient. So what we have done is we have made use of tidy graph and ggraph, and we plotted something of this sort. But then also it was cluttered, so we made use of some theme and also added some few layers and made this a little more attractive, and that's how we got something of this sort, right? So network visualization in general, it should basically highlight what are the key actors and links in that network. It should also show the relationship strength. It can show the structural properties, but right now it doesn't show any of those things. It is just showing some actors and links, and also we don't know uh, basically what are the structural properties and all these things, right? And when you talk about network visualization controls, color has an important role, position has an important role, size and shape of the nodes and edges which we are using, that also has a definitely has got a significance. And in addition to that, the arrows or the connection which happens between that, that also has a significance, right? And here, if you remember, we had made use of something called AES. It is nothing but aesthetics which we are applying in that edge. In the same way, if you wish to add some aesthetics to any of the nodes, that can also be done. So in the handout, I've given some layout aesthetics. For example, how do you prevent overlap, or making sure all edge are of uniform length, and how do you create a symmetric uh, social network or symmetric network. So you can make use of these aspects as and when required, right? So till now what we have done is we have made use of some uh, default data set, and on top of that we just worked on the things, right? So now what we're going to do is we will try to import some data from a source, and then uh, try to kind of make that into a network, right? How to do that? So for that, in your meeting chat box, you can go to the second link. There you can find two different files. Maybe I'll just open it for you, right? So there are, sorry, four different files, and you can download that onto your, so let me just download it. um, I'll just create a folder here. Each of those things, I'm just downloading it here. All the four data sets I've just downloaded to my system, right? I've created a folder and I've downloaded. That's what I've done. Now let me go back to my POSIT console. So basically I should have these things accessible inside this, right? So for that I can click here on this upload. I can choose the file which I've just downloaded. So here I have this thing workshop. So each of these data set, let me just put it here. So I got the first data set in my console in my working space here, right? You can see the pointer, mouse pointer. And next I'll just go for the next data set. And finally I'll just, so all the four data sets are now in my console, right? So now once I've successfully done that, what I need to do is I need to uh, take these data sets onto my console, right? So let me just clear off what I've done till now. It is cleared. So I'll just create an object with the name notes, and then I'll make use of a function called a read.csv. So the four data sets which we have downloaded, uh, we'll just take a look at that. If I just click here, view file, I can view that. See here, you can see all these data, it is separated with a comma. So that's why you call this as comma separated values, CSV. So here you have the column headers like from, to, type, and weight. So earlier, if you remember, we had this from and to alone. But if I want to create a directed valued networks, so I have those values also here. So how do I convert that into a graph, or how do I convert that into a network? That's what we're going to see. So here I'll just call this read.csv file. And inside that, I'll just mention, uh, I'll just copy this from dataset media notes, right? I'll just copy the file name from here so that I don't make any mistakes, typing mistakes. So initially notes are required, dataset example. I just copy this whole thing here, not renaming it, just copying it. Yes. And I will say I need the header to be true, and as it is, let it be. I don't want to do anything on that, right? Now if you observe here, I have an object in my workspace. So I have an object here, notes ID, media type, type label, audience size, right? Fine. And in a similar way, I can also import the link edges also, right? So read.csv and dataset media edges, right? So if I want to see how this notes and links looks like, I can always use the head function just to see. And you can see here, earlier this kind of links or edges file we have seen earlier also, from and to. But here in addition to that, you have type and weight. So this could also be used as like the weight, especially if you have a valued network, you can use that. And the the nodes part, you have some details regarding the each of the node and what type it is. Some things are newspaper, and maybe some things TV, like that. You have a lot of data, right? Now from this, first we'll create an iGraph object. So these iGraph objects here, earlier case we have created the nodes as well as the corresponding links in a single data frame. Now in this case, you have nodes as well as edges in two different data frames, one in nodes and the other one in links. So in that case, how do I create that, or how do I put that into this iGraph to create that one iGraph object, right? So graph from data frame, I would say, and here I would say D is equal to links, and vertices, that is also another parameter. Vertices is equal to nodes, and let it be a directed graph. So directed is equal to T.
Sir, will this work? Will this function work without creating a data frame first?
Here we already have the data frames. One is nodes and the other one is links. So what we have created in the previous thing, no, here we have used just after reading from that CSV file, automatically it is stored as a data frame. Both links, I hope you can see the pointer. Both these links, let me just highlight it. The nodes as well as links. These two data frames already we have created,
Okay.
right? Yeah.
Okay.
So that we are just mentioning here, D is equal to links and vertices is equal to nodes. From two different data frames, how we can create a graph, right? Okay. So now it has created a graph, I guess. I can try plotting it, but plotting will be a cluttered one, I feel. Aha. It's a highly cluttered. Uh, I don't understand anything over here. So one thing you can do is, if I want to see the edges of this object net, I can just call E and then net. Will give you all the kinds of edges, like you have from 01 to 02, then you have 01 to 03, 01 to 04, like that, all these edges. And if I want to see the nodes or vertices in that network, I can just call V of net. You have around 17 vertices, right? And specifically, if I want to understand the attribute related to a vertex, so imagine that I have V of net, and then if I put a dollar, sorry, put a dollar outside, uh, media, right? From where did I get this media? So if I'm just checking this here, you have this entity media inside nodes, right? So for each vertex, this media, that information is attached along with that node or vertex. So now if I want to know what all media is related to different vertices, I have all these things. Some of them related to New York Times, some of them Washington Post, some of them CNN. So different things are there, right? And also in the same way, if I want to know more about different mm, maybe different type dot label, I can even get that, right? And also at the same time, imagine that I want to view only those things related to a specific media. So which means that vnet, and in bracket, if I can just, I'll just say sorry, media is equal to BBC. So then that can return only those vertex which has BBC in that. So which means that S11, that particular vertex is related to BBC. Right? So in this way, I can extract only those required nodes or only those required edges as per my choice. Right? So imagine that I want to know for the first maybe for the uh, if I want to, basically this is a network matrix, and if I want to uh, know that uh, know more about the network matrix, I can just put here net. You have this matrix here, and if I want to view it in a proper matrix form, I can even do that. I'll just say net, Here we go. So you have the matrix here for the S01 to which all it is connected, and S10 to which all it is connected. So just remember the picture which I've shown inside the slide earlier. So wherever you have connections, that will be filled. So here what I've done is I've just called net, and within bracket I just put a comma, so that it will return the whole matrix as it is. Now if I want only the first row alone, right, I can just put here net 1. So you can see uh, what all it is connected, right? And if I want to know only the first column, I can just put comma 1, right? So this is part of the basics of R. So I'm not going into like how you can get or show the required data from a data frame. I'm not going into that. Now, if you typically want to see this as an adjacency metric, there is also a function called as underscore adjacency. So because here, if you observe, I don't have any headers here. So for example, here, I don't have any header, right? So if I want the typical adjacency matrix, I can also go for uh, the the function as underscore adjacency underscore matrix, and here I can just give net, and the attribute I want to consider here, that also I can mention here. Here I have weight here, so that weight I can mention here. Attribute is equal to weight. So it is suppressing some of the columns. I think I need to mention. Uh, we'll just take a look at as underscore adjacency underscore matrix, converting a graph into. So we'll just take a look at the parameters. Whether are we missing something? We'll just say names is equal to true. Let me just say okay. So the intention is, if you want it as a as an adjacency metric, you can go with this function also. Right? Now, right. So we'll try to plot this, and as you can see, if I don't let me just try to plot this graph. Net edge dot arrow size edge dot arrow dot size is equal to 4. Vertex dot label is equal to na. Still, I'm getting a very cluttered graph if I'm trying to plot the whole of the thing, right? So you can even remove any loops in this existing network if you wish to do so. So what I'll do is I'll just simplify this network. Just call the the method or the function simplify from igraph, and I'll just add net and remove dot multiple. Wherever I have loops, that also I can remove dot loops equal to t. So this is just to make the network simpler one, but I have other methods using which I can plot it. But still, using these methods, how do I plot a simplified graph? That's what I'm trying to show here. So net Okay, I have a simpler graph, but still maybe still it doesn't give me a better one.
So I think there's a
Yeah,
problem with, because you're doing on the cloud. I'm getting a very simple graph when I'm doing it on R.
in normal R,
Yeah,
but here also I should get the same thing. One second.
maybe if you try to zoom on it.
One second.
No, not here, in the plot itself.
Yeah, 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 understood, understood. No, if I'm clicking on zoom, it is going to a different window. One second. No, maybe or else I would have missed something in the code. We'll just redo that. One second, one second. Just creating another object net2, and here I'll just simplify that. Dot net size is equal to 0.3. I'm just giving, but text dot label. Yes. Yeah, I got a simpler graph, but still it is not the best one, right? So, so now what we have done is we have kind of created a particular yeah. So we have imported some data and then we tried to plot it. So what we are going to do is we'll try to add this to a second data set where you have links between news outlets and the corresponding consumers. So that those two data sets also we have already put it here. So that I'm just to save time, I'm just copy pasting it from the handout. So those two also I've just put it here. So the kind of graphs which we have plotted right now, those are known by the name unipartite graph, or it is a single mode graph where you are looking only at on one aspect. You have only maybe nodes and edges, and you have only a single graph. But if you wish to take a look at, or if you wish to have um, an adjacency matrix for a two mode network, so where you have two different types of actors and link that go across, but not within each type. So the second data sets which we have exported, or which we have imported, that has links which examine details or information regarding news sources and their consumers, right? So we'll just take a look at that also. Head of notes 2. So you have media name and the corresponding audience size, right? And if I'm taking a look at links 2, so here you have the edges, right? So in the earlier cases, in addition to that, here you have a like a bipartite network, right? So this usually you call it as an incidence matrix, what you see on. So why we are taking a look at in these two data types is that these two are very common. So in case if you are coming across the normal adjacency matrix, that is perfect. But in case if you don't have that, then there is every possibility that you may get data in this format as well, right? So we have already seen how to plot graphs with iGraph, right? So the earlier graph, for example, I can even plot it in a different way. You can find it in section 4.3.2 in the handout. I can even make it better, right? So if I zoom in, I get a very readable graph. Of course, the edge, I mean, the arrow looks a little absurd, but other than that, everything is okay. Now I can add a lot of other parameters also onto this plot, right? So plot net2, I just edge dot arrow size equal to, I'll just make it as 0.2, and edge dot color, I will, yes, maybe red. I can even give the corresponding color code of that I mean of that color. So how to find out the color code? You can just Google color code hex. So here, if you just go here, you can have different colors, right? So you just pick here, and the corresponding color, if I want to take, just copy this hash cc double f, and that you can just put it, color is equal to that color you can put there, right? So text dot color, I'll just copy that. I don't know final output how it comes. And the vertex dot label. So each of these things, what you are using here, you can you will be able to explore those parameters. Let's make use of net2 dollar media. Oh, sorry, dollar.
So what library is this function using?
It is using the plot function only. Inside plot function, we are just adding some parameters. The same plot function, but we are using extra parameters. And maybe vertex label, we'll put it as black. Label dot color. That quotes. Somewhere I have messed up. Size equal to 100. It's got color red. Okay. I have orange, that color. I haven't closed the arrow. That's the reason why. Here, there is a mistake. Yeah. So if I'm, so it looks like it looks pretty odd because I've given some bright colors. But what I'm trying to show here is I can edit these, each of these entities or parameters as per my wish, right? So I can also set these labels in a separate thing also. You can find that in section 4.3.2. I'm not going into that. And you can even put different colors based on some condition. So that also can be done, right? And right now, whatever we are plotting, we are not mentioning any sort of label, right? So imagine that you want to uh, plot set of random nodes and edges right over here, right? So I can just call the function sample underscore PA, will create some random graph which will follow this preferential attachment, which is part of this Barbasi-Abbott model, right? So in that way, I'll just show you different kinds of network layout, how it happens. So let me just plot one such thing, sample underscore PA, and I'll just go for 100 nodes, right? Let us create a highly cluttered one. And okay, maybe here also I need to specify the each of those things. So better I'll create that. So I'm trying to create some random network just to show you different network layouts, right? Sample underscore PA will go for 100 things. So of net.bg. Here earlier inside the plot I have given these parameters. Now separately if I want to give, how does it work? So I can give the size to be 8, yes, and the frame color or the overall color and the label, what all you need, all these things can be separately given in the same way. Just to save time, I'm just putting it together. And the edges, what should be the arrow, that also I can say. So net.bg dollar arrow dot mode, that I'm just giving 0, no arrows. Now if I plot net.bg, I'm getting a network of this sort, right? Now here I can also try out different layouts. So inside plot function I can just say net.bg and layout, sorry, layout is equal to, I have different layouts, right? So earlier, if you remember the KK thing which I have mentioned, so that comes from here only. So right now I'll just go for layout underscore randomly, and I have missed that parameter, layout equal to layout underscore randomly. Yeah. Now it has gone for a some random layout. So again, if I'm trying this, I may get a different layout. Yes. Now I've got a different one. So you can play around with these things as well, right? So now we have created a network. How do I measure or analyze the different network properties that are available, right? So in order to do that, I can just apply the different functions. So imagine that I want to find the degree centrality, right? So in that case, I can just go for the degree. So for example, uh, I want to find out the degree centrality of a graph. So degree underscore centrality, sorry, degree underscore centrality, and I want to find the degree centrality of the earlier graph. So net.bg. So now if I print degree centrality, for each node, what is the degree centrality it has calculated, that you can see in the form of a matrix. Right now, if I want to find the degree centrality of the earlier some of the graphs, so degree of G or degree of G2, which sorry, G2, which I've created, I believe. Yes. So for all these things also, I'll get the different degree centrality, right? Now, let's say if you want to find the betweenness centrality, then I can go for the function betweenness centrality, betweenness of, let's try for net dot bg, right? It's giving me the betweenness centrality. Now there are other centralities such as page rank or eigenvector centrality. For that also you have the default functions, which is part of eigen centrality, yeah, which is part of the iGraph. And here I will just say net.bg. Sorry, we'll try that for just the other graph. Needs some mathematical, yeah. Yes. So for 10 vertices, and before that we had created something with 100. So for that also, yeah, you have all these 100 values. For each of these nodes, it will create the centrality. And out of that, if you want to find out which one is having the maximum, right? And based on that, you can take some decisions also, right? And if you want to highlight certain aspects of the network, so you can find it in under section 6, that is highlighting aspects of the network. I can even try out, say for example, I want to identify the type and size of nodes, but cannot see much about the structure. So if the links are so dense, in that way, you can maybe keep only the important edges and you can discard the rest, right? So all these things could be done here. For example, if I want to do mean of links dollar rate. So the earlier links, whatever we have done, like whatever we have imported from the data set, right? So if you want to find the mean or standard deviation, all those things can be very easily done, right? So I can even, I can say that, say for example, I don't want any any node with say uh, with less than the mean value, right? I don't want any links to be there, right? So in that case, you can very well do that as well. So for example, if I can uh, I can, whatever I'm doing, you can find it under section 6 of the handout. So cut off mean of links dollar weight. How do I kind of remove certain nodes based on some criteria? That's what I'm trying to show you. So net.sp is equal to delete underscore edges, also part of iGraph. So I'll try with this net, that particular graph, and condition here is the edges of the net, it should be the weight should be greater than whatever value we have calculated, right? That I've, oh, I'm sorry, net.sp, it should be typo, it should be a hyphen there. So net.sp, and then now I'll plot net.sp, and layout I'll give layout is equal to layout underscore width, and try any other layout also. I'm just going with a layout with underscore k. So you have this kind of, because I've removed certain edges where the weight was less than that, right? So you can add colors also as per your choice, right? Which we have earlier done. So, right. Now, sometimes you want to highlight only certain nodes and not all the other nodes, right? So that is also possible. based on some conditions. If we want to focus on particular node or group of nodes. For example, in this data set, media network, we can examine the spread of information from certain nodes. For instance, we'll represent that like which media house like kind of is more important and which one is not more important, right? So based on some parameter, we'll try to do some analysis, right? So you can find whatever I'm going to do now, you can find it in section 6.1 of the handout. I'll just clear whatever I've done. So I'll just create a metric where I'll try to uh, find the find it using a function called distances. What this distances does is distances. Sorry. So this actually calculate the kind of shortest path from a particular node. So we'll make New York Times as the node under consideration, and from that, what is the distance to each of the other nodes? That's what we are trying to find, right? So dist dot from dot nyt. That's what we are trying to find. So we'll make use of this distances function, which is part of iGraph. So distances, and the graph under consideration is net, which we have already built. Maybe we'll try with net 2. V equal to V of net, and we are gonna consider only the media equal to ny underscore ny times, and 2 is equal to V of net. Here I'm not going to consider any weights. Uh, weights is equal to na. Okay, I have some one extra bracket over there. That is the reason. Let me just right. Okay, so list from NYT. So the distance from uh, New York Times to all the other nodes, that's what is being represented here. So S01 is the New York Times, that particular vertex, right? So, and we'll create a color palette to plot the distances. I'm just naming that as oranges. So color ramp palette. Here I'll just mention only 2 colors. Maybe we can light red and maybe gold. Okay, I don't have light. Maybe I'll go for dark red then. That worked. Now, so what all will be part of oranges? That's what I'm trying to find here. Maximum, the max value from that New York Times plus 1 we'll put. Those things will be what whoever is closer to New York Times will be in one color, and whoever is farther from New York Times, that will be in a different color. That's what we are going to do here. And again, the other colors will be just from Now let's try plotting this. So we'll consider net2 vertex dot color is equal to COL, and vertex dot label is equal to distance this dot from NYT, right? And edge dot arrow dot size is equal to 0.4, and it's not mandatory to give all the parameters. Even if you skip some of these, it is perfectly okay. But text dot label dot color is equal to white. No, I think I have yeah, I've made use of net only. No, somewhere I messed it up. Here I've used net2, but here I've used net. Okay, that was the reason. Okay, let me just rectify that. Where I'll make it net2, and okay, rest of the things anyway, I don't have to make any changes. The same thing I'll run, and when it comes to plot, let me just try this out. Here, let it be net2, or something, but the colors are not reflected, I guess. Yeah. Fine. Right. Uh, so the intended output was you should be getting it in as in the handout. I'll just show the handout here. Yeah. So this was the expected thing, but I think I messed up in the code somewhere there, and where right now we don't have the time to debug, so I'm not going into that. So in a nutshell, what we can do is other than having this static kind of network layouts, you can also go for interactive or dynamic visualization also. So especially there is a lot of significance for such kind of networks. So in order to help you to achieve that, you have a package called a vis network, which will help you to create uh, networks of this sort. For example, I can just change it in this way. I'm just dragging and dropping, and that is just creating me or giving me the network, right? See, you can see it is very interesting. I can just push it, and still again it will come back to this position, right? So that can be done using this library of vis network. So let me just go back to the console. We'll just try that also, and then maybe we'll wind it up. So just trying out library of vis network. For that I need to install that. I'm sorry about that. Vis network. So I can just install. It may take us a little time. Maybe in the meantime I'll show it in another console. uh, okay, it had started. So we'll just wait a couple of minutes to get it installed. Yeah. Yes, it got installed. So I can directly call library of this network, and we'll make use of some existing data set to get it plotted. We'll just call the vis network function, and the nodes and links, if I'm just giving, gives me a plot which is very dynamic. So you can see here, I can even try that with maybe nodes 2 and links 2, whether it will, yeah, it is completely, as I mentioned, it is a bipartite graph, so that's why it is being shown here. um, okay, so I can also specifically add some uh, parameters on top of this also. So with network nodes and links, I can mention, say for example, if you want to deploy this onto a web page or something, this kind of a thing, I can even mention what should be the height uh, of that whole network, what should be the width in which it should be displayed. I would just say it has 100%, and let's say background you want some color. I would just put any some color. Okay, and I can even put some name for the network. So main is equal to network on this work. So it gives me a right. So I'm getting a very dynamic one, right? So if you add more colors or labels onto this, it becomes even more interesting. Such kind of plots I have shown it in. I haven't shown the code because I don't want to give too many things in a single session. So if you can see here, this is the one which is once again, which is plotted in your handout. Let me just zoom out so that, yeah, so you can see here I can just move this in any way I want, and even if I'm moving still, for example, if I'm clicking on something, I'll be able to know which all it is getting connected, right? I can just like move it, and here for example I can even kind of sort it with different sorry, it is a down one. I can even sort it with different things. Say, for example, if I want to kind of differentiate between the various media houses, online, newspaper, and TV, I can even do that with different notes and get a very good interactive plot, right? So, in addition to this programmatically creating this, there are other tools available such as Gephi and all, which can drag and drop the data and it will give you the things. But the limitation of those interactive drag and drop tools is that you may not be able to customize something. If you want to do research on social network analysis and you want to customize something, you may not be able to achieve that easily, but programmatically you will be able to do so, right? So I guess with that, uh, I think we'll call this session. I mean, we have come to the end of the session. So to work on with, I've also given put an assignment here. You can find, you can just click on the link that will ask you, 1 second. I think that assignment link, let me just put it here. That's what I'm trying to put, or connect. Okay, I'll just put the link once again. You should be able to see this assignment. So I've also given some more data sets. So just you can try plotting the graph from these data set, and also try calculating the centrality measures and displaying that. You can plot an interactive graph, and also plot the data using different layouts, at least maybe 5 or 6 different layouts if you can try out. And uh, you can again go through the handouts if required. uh, you can very easily complete it maybe within an hour or so, right?
Ex- Hello,
Ye-
sir.
yeah,
Yes.
yes, please go ahead.
Sir, I'm not able to access the data. It requires permission.
One second, one second. Just give me a minute, I'll just provide it. Can you try refreshing? I mean, now you should be able to access,
Yes, sir.
right? Yeah. Yes. Fine. So if there are any questions, I'll be happy to take that. Else, maybe we'll wind it up. Okay, I assume there are no questions. Again, you can still take a look at these handouts, and also go through the data sets, and also the recorded video will be shared, I guess. And thank you for listening, and also wish you a great day ahead.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, everyone.